Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're going to be looking at catalytic hydrogenation. That is the addition of H2 gas to alkenes and alkynes. In fact, H2 gas in the presence of a catalyst can add to a variety of pi systems, including C double bond O, C triple bond N, as well as alkynes and alkenes. In fact, you can selectively vary catalysts so that you can hydrogenate alkenes and alkynes, but not C double bond O's, or an alkyne, but not an alkene. Catalysts come in two varieties. They are either heterogeneous catalysts or homogeneous. Now, heterogeneous catalysts are two-phase. That is, the catalyst is not soluble in the solvent. It's usually a finely divided metal, such as platinum or palladium or nickel, although there are others. The solution of alkene is in an inert solvent, shaken under slight pressure of H2 gas in the presence of this metal. And when the reaction is complete, the solution of saturated product is filtered from the insoluble catalyst. So it's very easy to separate the catalyst from the product. In homogeneous catalysts, the catalysts are organic complexes of transition metals. You may have some kind of rhodium or iridium compound. These compounds, called complexes, are soluble in the solvent. They dissolve in the organic solvent. And so the reaction takes place in a single phase. That is, both catalyst and reactants are soluble. Remember, in a two-phase catalyst, the catalyst is insoluble and is suspended as a finely ground metal in the solvent. Now, hydrogenation can work with homogeneous catalysts, but there usually is a problem in separating the catalyst from the product. Problem, and I'm going to just put an arrow and I'm going to say separation. It can be difficult to separate your catalyst from your final product. So homogeneous single-phase catalysts have a disadvantage. However, typically homogeneous catalysts are more selective. In fact, you can get them so selective that they can sometimes even generate or be designed to generate individual enantiomers. That level of selectivity has not been generated in heterogeneous catalysts. So what is the mechanism of heterogeneous? Let's focus now on heterogeneous catalysis. Previously in our course, I have mentioned platinum, palladium, and nickel and described them as sponges for hydrogen. In the same way a sponge can soak up water and remove water from a system, a sponge that is wet can be wrung out and made to deliver water. Well, platinum, palladium, and nickel essentially can do the same thing with hydrogen. In the presence of hydrogen, they can add hydrogen, and that's what we're going to look at. What happens to pi bonds when we add it. But in the absence of hydrogen, platinum or palladium or nickel can scavenge hydrogen from alkanes and prepare alkenes. Let's consider hydrogenation. What happens when platinum or palladium or nickel is in the presence of hydrogen? In the first case, the H2 molecules are adsorbed on the metal surface. Now, we used the term adsorb before in thin layer chromatography experiments. What is the difference between adsorb and adsorb? Well, absorb is easily translated as soak up, to draw into. Adsorb means that the H2 molecules adhere to the surface. So if I have a metal surface, I'm going to use this. Let's use a different color to represent my metal surface. The H molecule weakly interacts through intermolecular forces with the metal surface. Point 2. The HH sigma bond is broken. And H metal bonds are formed. And H metal so you actually form metal hydride. So we go to our metal surface, and now we have hydrogens bound to the metal. In step 3, adsorbed alkenes or alkynes so either alkenes or alkynes have pi bonds that are broken. Pi bonds are broken. And pi electrons bond to the empty orbitals of the metal. So if you like, pi electrons bond to empty metal orbitals. So if I was to continue my metal surface, we not only have HH bound to the surface, but our alkene, right, has come in, the pi bond is broken, and it's interacting through the two p orbitals and pi bonds. And it's on the surface. Finally, in step 4, the alkene molecules and hydrogen atoms are surface mobile. That is, they move around the surface. They are surface mobile. The alkene moves along the surface of the catalyst until it collides with an H atom. So H and C collide. The H atom is transferred one at a time to an alkene. One at a time. One at a time, making CH bonds. So one at a time, they collide, you make CH bonds. And once the alkane's formed, alkane leaves. Leaves the catalyst. So how would this look? Well, next they collide, and what you get then, still have an H bound. Now you have the CH3. Until finally the CH3 leave. Now the interesting thing to note is I'm going to actually use a different color for these H's. And the point I want to make is that they're actually going to go on cis. And there you go. Those H's actually go on cis. So we get Syn-Addition because they go on the same side of the alkene. So because the reaction takes place at the metal surface, you end up with what is called Syn-Addition. And we've mentioned Syn-Addition before. Okay. So let's look at some examples of this hydrogenation reaction. Well, for example, I can take an alkene like this that has maybe 2 bromines off of it. So 1,2-dibromocyclohexene. I'll put dots to show the carbons. This is a hexene. If we take this with H2 gas, so I hit it with H2 gas, and we're in a catalyst, I could use platinum, or I could use nickel, or I could use palladium, so I'll vary the catalyst. I get a cis-addition product. So I'm adding, I get cis 1,2-dibromocyclohexane. The hydrogen adds via Syn-Addition. So I get cis-only product. A cis-alkene is made. If you try to do the reaction on an alkyne, it's very difficult to control. Suppose I take alkyne and I just apply H2 gas and platinum catalyst. I'm looking for something I want to talk about. Of course, I don't see it. It should be here. Okay. If I hit this with H2 gas, and just platinum, it's very difficult to stop it at the alkene. You will produce alkene, but the hydrogenation is so efficient it goes right through the alkane. The alkene is produced, it's hard to stop. This reaction will produce alkane. Yes, you go through the cis-alkene. You still get Syn-Addition. But in actual fact, it's very hard to stop. Now I have a description here of a catalyst. Oh, there it is. That will allow us to actually take the alkyne and stop at the alkene. The trick is to poison the metal catalyst. Suppose I can use one of two methodologies for deactivating the catalyst. Suppose I hit this with H2 gas and I use palladium with quinoline. What is quinoline? Well, it turns out that quinoline is a molecule that looks like this. Let's make it a little, there we go. And the nitrogen can bind to the palladium through its lone pair. And the quinoline can interact with the palladium and hinder its interaction so that it stops at the alkene only. So palladium and quinoline gives you the cis-alkene. Another reagent that would do this the same way is to use H2 gas, but instead of quinoline, replace the quinoline, palladium quinoline, and we could use a palladium catalyst that has been poisoned by lead and calcium carbonate. If you use a palladium, palladium lead, lead, calcium carbonate, you will also stop at the alkene. Both catalysts work. So watch for that, palladium, lead, calcium carbonate, or palladium and quinoline. These are catalysts that have reduced activity and will react, yielding cis-alkene. Well, it would be nice if we could somehow not just make the cis-alkene, but we could make the trans-alkene. Is there any way of taking this alkyne and not getting Syn-Addition? Because if you're making alkene and you get only cis-2-butene, well, as it shows, that's Syn-Addition. Is there any way to get anti-addition to a pi bond? And the answer, of course, is yes. We can take this alkyne and we can hit it with sodium metal in liquid ammonia. Be careful. This reagent looks a lot like, well, what does that give us? That gives us the trans. Sodium is reducing, reduce the alkyne to an alkene, but it goes stepwise so as to give us anti-addition, or the trans-2-butene. Be careful. All right. This is a lot like the reaction used to make this alkyne. What do you mean? Well, I'll make some room here, and I'll write this in red so you can contrast it. This reagent, if I took CH3, CHBr, CHBr, CH3, if I hit that with sodium amide in liquid ammonia. That's liquid ammonia. And then 2H2O. Sodium amide's powerful base will do a double elimination to make the alkyne. Notice that sodium amide NH3 liquid looks a lot like sodium in liquid ammonia, but they are different. This is sodium metal, not sodium NH2 minus. So be careful. We learned this in the preparation of alkynes. Don't confuse the two reactions. Okay, some reactions of alkenes. Hydrogenation also can be used to help us to determine stability of alkenes. And the rationale is quite simple. We've already examined that when you take an alkene, any alkene, and you react it with a molecule like H2 gas, the reaction is exothermic because you're breaking a sigma bond and you're breaking a pi bond. Now, pi bonds have side-to-side overlap that's not as efficient as sigma. Sigma bonding is the orbitals directed at each other, you get better overlap. Better overlap means stronger bonds. Sigma bonds are stronger than the pi bonds. So because of that, there's more energy released when they're formed. So if you break one sigma and one pi, you have to put in energy. But then you form two sigmas. Well, forming two sigmas will give back more energy than breaking one pi and one sigma. The net reaction is you get back more energy, you get energy release. Delta H is negative. Reaction is exothermic. So if I made a plot, okay, a plot of energies, alkanes come at low energy. Suppose this is the position, this line represents the energy of the molecule butane. Hydrogenation is the methodology we use to experimentally identify which alkenes were more stable. Remember, we said that 1-butene is less stable than 2-butene. Let's draw 2-butene over here. Here is the energy level of 1-butene. Here's the energy level of 2-butene. When you hydrogenate, you can actually, when you take the alkene and you hydrogenate, you can measure how much energy is released. The delta H for taking 1-butene to butane is 30.3 kilocalories per mole. That can be measured by hydrogenation. 30.3 kilocalories per mole. Okay, so all the values are in kilocalories per mole. 30.3. We're releasing the energy, so it's negative to become butane. What's cis-2-butene? Cis-2-butene releases 28.6. Now they both form the same thing. That is, they both form butane. And so the butane formed from 1-butene and the butane formed from cis-2-butene is the same molecule, has the same energy. So the difference must be in the position, how high up you are. So if you're 30.3, that means 1-butene is higher energy. Higher energy means it's less stable. What's the energy for the trans? Well, the trans was 27.6. Trans-2-butene, when hydrogenated, had a energy release of minus 27.6 kilocalories per mole. This shows us how the stability of these alkenes were determined. You know, for example, the Zaitsev rule. The Zaitsev rule says less substituted alkenes are less stable. More substituted alkenes are more stable. This double bond only has one alkyl group, one electron donating group. This double bond has two electron donating groups, two methyls. Well, Zaitsev rule says more substituted double bonds more stable. It was hydrogenation experiments that measured the energy, and since they all produce the same alkane, the energy difference must be attributable to the stability of the alkene. So hydrogenation gives you the stability of the alkene. And the less substitute alkene was indeed less stable. We've also said trans alkenes are more stable than cis because in cis you have more repulsion between these groups. That is evident from the hydrogenation. Both two butenes give you butane, so any difference in energy must be the difference between the cis and the trans effect. So hydrogenation values can be used this. Now I don't expect you to memorize these values. I will give them on a quiz if I need you to answer a question about this. But you should be able to explain how hydrogenation can be used to experimentally show which alkene is more stable. And the reason hydrogenation works is the hydrogenation of different alkenes, 1-butene, cis-2-butene, trans-2-butene, all produce the same alkane, butane. Butane exists at one energy level. So any difference in energy release must be due to the energy of the alkene. So hydrogenation works really nicely this way. We've also mentioned stability differences between conjugated and non-conjugated double bonds. For example, conjugated double bond systems will better delocalize electrons. We've drawn this type of thing where we've had conjugated double bonds. And we've said, look, when you have a pi system here, that makes your double bond. And you have a pi system separated by one single bond. The side-to-side overlap makes you double bonds, but this pi system and that pi system can have side-to-side interactions. That allows electrons to completely delocalize between the two double bonds when they're conjugated. This extra delocalization leads to stability. Well, that's a theoretical explanation, but how do you check it experimentally? Well, we know there's some energy for pentane. We can take a molecule where the double bonds are not conjugated. We can, for example, take a molecule that has two double bonds, like 1,4-pentadiene. Now this molecule is not conjugated because there are two sigma bonds, two single bonds between the double bonds. So these are called isolated. If we measure the energy to hydrogenate both double bonds, it is exothermic, minus 60.8 kilocalories per mole. Now try and do it for a conjugated double bond that will also give pentane. If we hydrogenate 1,3-pentadiene instead, do add 2 H2 molecules, completely hydrogenated, you'll get pentane. But the energy released this time is only 54.1, and so it's negative because the energy is released. So 1,4-pentadiene gives more energy. They both form pentane, so there's no energy difference in the product. So the difference in magnitude must be due to the position on the energy scale of the non-conjugated versus the conjugated. The conjugated is more stabilized. We explain that stabilization by delocalization of electrons through the pi system. So hydrogenation of alkenes can be used to explain different stabilities, which can be extremely useful. The last point I want to make about this whole hydrogenation process is the importance of the catalyst. If I follow the energy of reaction, so this is energy, and this is the progress of the reaction. Sometimes it's just called time. And we start with our reagents. Our reagents, of course, are the alkenes and hydrogen. Okay, and we get our products. Our products will be the alkanes. They're lower energy. Let's consider first what would happen if we try it with no catalyst. If we try it with no catalyst, we get a huge activation energy. A huge activation energy. H2 will not react with alkene in the absence of catalyst because of this huge energy of activation. But when you react with a catalyst, the energy of activation is reduced. And remember, the catalyst, of course, in our reaction may be platinum, or palladium, or nickel. The energy of activation is lowered sufficiently to allow hydrogenation reaction to occur. In the absence of a catalyst, there is no reaction with H2 gas. How does a catalyst lower the energy of activation? Well, remember, the reaction is not between H2 gas and the alkene. It's between the hydrogens attached to the metal. Remember, the hydrogens bound to the metal and the interaction of the alkene on the pi surface, or through the pi bond interactions with the metal surface. And this could result in rehybridization, where they become sp cubed instead of sp squared. So this may rehybridize. So the alkene binds to the metal surface, the hydrogens bind to the metal surface, and now the energy of reaction is between a metal hydride and a carbon metal bond, not free alkene and hydrogen. So catalysts work by lowering the total energy of activation. The addition of hydrogen, of course, represents reduction of alkenes. What happens if we attempt to oxidize alkenes. Let's take a look at what actually can happen if we attempt oxidation of alkenes. Now, oxidation can essentially take place two ways. You can try mild oxidation, where you control the oxidation reaction and you don't let it go too far. Or you can let the reaction go extreme and actually cleave a double bond. We're going to begin by looking at mild oxidation, or what is sometimes called diol formation. Okay. So oxidation of alkenes and diol formation. All right. Diol formation is the direct addition of two OH groups to the two carbon atoms of the double bond, sometimes called hydroxylation reaction, and is carried out using metal oxidants. So if I take an alkene like cyclohexene, I'll put dots here just so you can tell it's a cyclohexene. Those are my carbons. And I react this with KMNO4. It's potassium permanganate, it's called. And base, cold, dilute, trying to keep the reaction from going out of control. Cold dilute. There may be H2O around as well. H2O is probably a solvent. We get Cis-Addition, Syn-Addition. And we get a 1,2-diol. Syn-Addition. Why would we get Syn-Addition? Well, the reason has to do with the permanganate. You see, when the double bond is attacked, it's actually attacked by a group, well, let's draw it here actually, that looks like this, the permanganate anion. These guys have lone pairs. And so the pi bond goes towards the electron on the oxygens. The electrons of the pi bond go to electrons. The oxidant dumps a pi bond towards the alkene, and these pi bonds create a lone pair. Get a circular movement of electrons. We're going to define this later. It's a paracyclic movement of electrons. And we go through an intermediate that looks like this. Oxygen, oxygen, manganese, lone pair, double bond O, O minus. We've got some lone pairs here. This is called a cyclic inorganic ester. cyclic inorganic ester. The hydroxide catalyzes the hydrolysis of the manganate ester. In other words, these two oxygens retain and form a diol, and we kick out the MnO2 solid. And hence we get cis-addition plus a brown precipitate, which is MnO2 solid. So the Syn-Addition occurs because of the cyclic inorganic ester. Now you should be able to draw the cyclic inorganic ester and explain why we get Syn-Addition. Okay, the same alkene can be reacted with a related group. Underneath manganese in the periodic table is osmium. And osmium tetroxide can be used to react in the same way the permanganate did. Osmium, when it attacks, looks like this. OSO4, osmium tetroxide. Very toxic molecule. So if I hit this alkene with, say, 1 osmium tetroxide, because it's so toxic, you'd normally use the permanganate. But you could use the osmium and hit it with the Na2SO3, sodium sulfite, and water. You will also get the diol. And Syn-Addition. Well, what if we want trans-diol? What if we want to oxidize an alkene and get trans-diol? Well, we can go to the trans-diol via a methodology we learned in alcohols. Actually, the epoxide section of the course. Let's take the same or a similar alkene. Let's take the same alkene. And we're going to react it with one of two reagents. We can use the industrial prep with oxygen gas over a silver catalyst. Silver is the catalyst and we use heat. Or in the laboratory, you're more likely to use peroxyacetic acid. This is very similar to peroxybenzoic acid. This guy's called peroxyethanoic or acetic. Peroxyacetic acid. Use either of those molecules and you will make something we've seen before. Cool. What's that guy? We make the epoxide. We make an epoxide or an oxyrain. Now, we've learned how in epoxide chemistry you can attack with acid or base. And if I use OH minus in H2O, or I attack it with H plus in H2O, well, in this case I'm putting the same groups on, so the site of attack won't matter. Remember, in base, we attack, the nucleophilic attack goes on the less hindered carbon. In acid, the attack of the water goes on the more hindered carbon. In this case, they're the same hindrance, and you're going to end up with OH groups at both positions. So they both end up going to the same molecule, which in this case is trans-addition, anti-addition of the diol. Why anti? Do you remember the mechanism? The mechanism for both attacks is SN2. The nucleophile, whether it's water or that, does backside attack. So it'll be up. And when this breaks, that guy will be down. So it must attack the side opposite of the epoxide. So the one is down and the other's up. So we never learned in the epoxide section how you make epoxide. So here we are in a reaction of an alcohol learning how to make an epoxide. And then that we can use it to make trans-diols. Okay. Now, both these oxidations are mild oxidations. And I say mild in that we only break the pi bond of the double bond. We're not breaking both the pi and sigma. What's interesting about these oxidation reactions, however, is that you can take them to extreme. What's that? Well, you can actually break the entire pi and double bond with these oxidizing agents. For example, we use cold dilute KMnO4 to make the diol. But what happens if I hit this guy with KMnO4 in acid rather than base? Okay, hot KMnO4. And I might put acid here. So I might put H+. Hot KMnO4. What happens is wherever there is a double bond, I split it and I put a double bond O. Okay? And then there's an H. Wait a second. H's get oxidized also and become OHs. So the H's, if there's an H off the double bond here and here, in KMnO4 hot, those H's become OHs. So this is a carbon, this is a carbon. I've split my double bond and I made a CO2H. So I'll show all my carbons. Count the carbons. What is that? 1, 2, 3, 4, 5, 6. So what is this molecule that I've made? Well, I've made this molecule. These two molecules are the same. I've opened up the ring. I've oxidized it and disrupted the pi bond. I've made hexane, 1, 2, 3, 4, 5, 6, hexane dioic acid by cleaving with hot KMnO4. Now what's interesting is if I compare this to say a reaction which has carbon. So let's make an alkene like this and do the reaction. Try to draw straight. A straight line can be the most difficult thing to draw. KMnO4 and heat. Well, wherever the double bond was, I break it and put a double bond O. So there's my double bond O from that carbon, and here's my double bond O from the other carbon. If there's carbons, they don't get affected. So it looks like I get acetone. But if there were H's, each H off the double bond becomes an OH. What the heck is this? Well, this is just carbonic acid. It's H2CO3, right? That's carbonic acid. And this molecule is acetone. Our alkene split down the middle and got oxidized. Well, there's another way of actually doing the same reaction, and it involves the use of ozone gas. Now, ozone is very important to the upper atmosphere. Ozone helps protect the planet from ultraviolet radiation. And we have in recent years been measuring the amount of ozone in the atmosphere, tracking what is called ozone depletion by pollutants we put in the atmosphere. Such pollutants have been banned, they have been refrigerants used in refrigerators, and they've been replaced. And there is some evidence to suggest that perhaps our ozone holes over the North and South Pole are repairing themselves. But ozone is a toxic gas. We don't want it at ground level. It's a very powerful oxidizing agent. Low exposure produces irritation in your eyes. Ozone can be made by electric discharge. Lightning bolts in the atmosphere can produce ozone. It can also be produced by the chroma wire used to apply toner on paper and laser printers. Many laser printers have cartridges in them that are filters for ozone, and you're always encouraged to use laser printers in well-ventilated rooms. The low production of ozone is only produced when you're actually printing and an electric charge is passed over a wire. Oxygen is exposed to that wire, and that electric charge can produce trace amounts of ozone, which can build up in a room and cause eye irritation and discomfort. So ozone, O3 gas, can be produced by taking 3 O2 gas molecules and applying an electric discharge and you get 2 O3 gases. Now ozone, I can draw several resonance structures for ozone. If I check the central oxygen, I will have lone pairs. And you can go home and try drawing the Lewis structures. So here is ozone, where it's not an acceptable Lewis structure, but it certainly is an acceptable resonance structure. I have a positive here and a negative here. Only 6 electrons around this. Certainly can dump in. There's a better resonance structure. 1, 2, 3, 4, 5, so he's positive. He's negative. And of course, can have the double bond on the other side. So here's the structure of ozone. Although it's not a resonance structure, and because it's a strained ring, it's not really called a contributor, but sometimes ozone is drawn in a 3-membered ring, strained ring structure. The formal charge of each atom is 0. This isn't a resonance contributor because you're not allowed to change atomic position in resonance structures. And we are shrinking this to make a bond, shrinking that angle to 60 degrees. Okay, we're going to work with these resonance structures, which are the main contributors. Now suppose I take an alkene, which has several groups. And suppose I bring one of the major contributors of ozone into proximity. Well, what certainly can happen is I can have electrons move this way, electrons move that way, electrons go here. I can get the ozone bridging what was a pi bond. This is referred to as a molozonide functional group. This quickly rearranges, okay, so that this bond breaks, and the oxygen inserts between the carbons, and you get this. It's an ozonide. Now, ozonides, high molecular weights are stable, but low molecular weights are explosive. So they're not usually isolated. Although these species form, you usually take them with another reagent and break these oxygen and oxygen carbon bonds, thereby separating the C double bond C. Effectively, ozone allows us to do exactly what permanganate does to a double bond. So that if I had an alkene like this, where the double bond was, I split it. Now, the advantage of ozone over KMNO4 is we can control what happens to the hydrogen of the double bond. If I use ozone in step 1 to make my ozonide, react it, and then immediately add zinc and acid, unlike KMNO4, yes, the double bond rips. Yes, I get double bond O's where my double bond was. But this time the H stays intact. It's called reductive ozonolysis, if you like, reductive oxidation. It slows down. The zinc prevents the oxidation of the H to an OH, and it stays here, and we get an aldehyde. But if we use ozone, and then in step 2 use peroxide and acid, then just like permanganate, the H attached to a double bond becomes an OH, giving us a carboxylic acid. But if there are no H's, you just leave the carbons untouched, and you only rupture the pi bond. Now you can get some very interesting products happening when you do reactions like this. For example, what if you have a fused ring like this, which has alkenes here and here? And what if you said I hit this with ozone and then to the zinc? What's nice about the zinc is it tells me immediately I don't have to worry about the hydrogens off the double bond. The H's would turn into OHs. But wherever there was a double bond, I break it and I put double bond O's. So here was a double bond, so I'm going to have double bond O's here. Here was a double bond, I'm going to have a double bond O here. The H that's off here stays an H. So that stays an H as well. And if I check this out, I get this real 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, let's draw this out. I get H, C double bond O. Right attached to this guy is a C double bond O. And then I have 1, 2, 3, 4 CH2s. This C double bond O. And then I get 1, 2, 3, 2 CH2s, and then a C double bond OH. Now aldehyde is higher priority than ketone. If I was to name this, this has 10 carbons. This is a decane. This is a decane dial, 110. I don't have to put it in 110 because the aldehydes have to come in at the end. This is a decane dial. Number from this end, 1, 2, 3, 4, 5, 6, 7. A 2,7-dioxo decane dial forms. Do I have to draw it this way? It's a straight chain? No, this top ring says the same thing. It's a line formula. It's perfectly fine. So you can get complicated structures forming under oxidative conditions. Well, that's reduction and oxidation, hydrogenation of alkenes, and the oxidation of alkenes. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.